हिंदुस्तान के हर कोने में नौजवानों के पास प्रतिभा है, उन्हें अवसर चाहिए।
NIOS देता रहा है युवाओं को अवसर आगे बढ़ने का। NIOS से पढ़ने वाले इन युवाओं ने किया है संस्थान को गौरवान्वित। दिव्यांगों ने बन के दिखाया है सबल और आत्मनिर्भर। NIOS के साथ आप भी जुड़िए NIOS के संग।
Hello learners, myself Dr. Alok Kumar Gupta, Academic Officer Physics, welcomes you at National Institute of Open Schooling, Noida. Dear learners, we are facing many problems regarding electricity, so we should save electricity. The phenomena related to electricity and magnetism is known as electromagnetism. You may have seen many electrical appliances like generator, motors, transformers, magnetic brakes, etc. These all are based on electromagnetism. So, for this discussion today our expert is Sri Sher Singh, head of the school, Navyug School, Lakshmi Nagar, Delhi. So, I welcome you, sir.
Thank you. The topic selected for discussion is quite interesting. The relationship between magnetism and electricity was discovered in 1819 during a lecture demonstration of Hans Ørsted. So, this demonstration done by Hans Ørsted we can see in our experiment, and let us do this experiment. Here we have a wire which is known as conductor, and we have a source of electricity and a magnetic compass. This magnetic compass will sense the magnetic field. So, I am putting this magnetic compass here and I will pass the current through this wire. Now, you can see the deflection in the magnetic compass. This deflection in magnetic compass indicates the production of magnetic field due to this current carrying conductor. If I change the direction of current, let us see again the deflection. When direction of current is changed, the deflection goes in opposite direction.
Sir, is there any rule to define the direction of magnetic field?
Certainly, when I am changing the direction of current, the deflection of the needle changes. It means the magnetic field produced by current carrying conductor is vector quantity and it has direction associated with the direction of current. And we can see in another experiment more precisely. Here we have a battery and a current loop, and we have made a system to check the direction of current. So, to check the direction of current, I have used LED, light emitting diode, which allow current to pass only in one direction. Here you can see this LED is glowing. So, current is in one direction, and now you can see the direction of current. Here this is positive terminal, so current is coming to this wire, this is positive terminal and it is going like this, then this. So, when I say this, from my side it is clockwise, from your side it can be anti-clockwise. Now, when we bring a magnetic compass near to this coil, let us see what happens to the needle. So, this is a magnetic compass. When it is placed in the magnetic field of the coil, you can see the deflection in the compass. So, again I am changing the direction of current. This terminal is connected to this and this, now reversed. So, you can see here now another LED is glowing.
Sir, why here 2 LED you are using?
We have used these two LEDs in parallel. In one LED, direction of current is this, and in another LED, direction of current is this.
This one.
So, one time direction, in earlier LED it was clockwise direction, now it is anti-clockwise direction.
Okay.
So, when we bring this magnetic compass again, you can see the deflection in opposite direction. And to know the direction of magnetic field, we use a rule, and that is a right hand palm rule. This is right hand, and we have to put our thumb in the direction of current, fingers towards the point where magnetic field is to be determined, and push of the palm will give you the direction of magnetic field. This is a very simple law. There are the other laws, Maxwell screw rule, Ampere swimming rule, to know the direction of magnetic field. So, this was the experiment performed by Hans Oersted, and on the basis of this experiment we can conclude current carrying conductor produces magnetic field. Magnetic field is vector quantity, change in the direction of current changes the direction of magnetic field. Now, let us have one step forward. It is very interesting to note that the same discovery was reported in 1802 by an Italian jurist, and this was overlooked probably because it was published in a newspaper. It was not published in a scholarly journal, so it was overlooked. Shortly thereafter, Henry Ampere obtained a quantitative law of magnetic force between current carrying wires, and he also suggests that electric current of molecular size are responsible for all magnetic phenomena. You can see Henry Ampere's law, how it is important. However, the phenomena of magnetism was known to the Greeks as early as 800 before Christ. They discovered that certain stones, now called magnetite, and chemical name is Fe3O4, attract pieces of iron. And there is a legend ascribes the name magnetite to the shepherd Magnus, the nails of shoes and the tip of whose staff stick fast in a magnetic field while he pastured his flocks. In 1269, the Maricord, using a spherical natural magnet, mapped out the direction taken by a needle when placed and at various points on the surface of the sphere. He found that direction form lines that encircle the sphere and interact the opposite ends, which are called the poles of the magnet. And very interesting conclusion is drawn after subsequent experiments showed that every magnet, regardless of the shape, has two poles called north and south poles, which exhibits force on each other in a manner analogous to electrical charges. That is, like poles repel and unlike poles attract each other. Here we can have one very interesting activity. This is an inclined plane. Now its inclination is fixed. We have a ball, and this is the rolling motion of the ball. This ball rolls freely. Another ball we can have, and we can see its rolling motion. Another ball we can have, Alok, you can provide this. Let us see two balls rolling down. Now, these are the iron balls, and this property was earlier known to the Greeks, that iron attracted by magnet. This ball is also attracted by magnet. It means this magnet attracts the iron balls. Now, let us place these two iron balls and a magnet here, and let us see what happens to these two balls. These two balls goes like this. Now I am using these two balls again, roll down. They are not being attracted by magnet, they stop somewhere else. They stop.
Sir,
So it is very interesting. Yes.
sir, why these two balls are not attracted by this magnet, and which forces are responsible for this phenomena?
So this activity shows the experiment fact which was earlier known to the Greeks. This is the magnet. This magnet is magnetizing this ball,
Okay.
and again this magnet is magnetizing this ball also.
Okay.
During magnetization, if this pole appeared here is north pole, then south pole will appear here, north here and south here.
Okay.
So in between, one pole is north pole and one pole is south
pole.
pole. These two like poles attract each other. So the system of these two balls becomes a single system, and this single system is not free to roll. Now it will slide, and you know that sliding friction is much more than the rolling friction. That is why these two balls are not attracted by magnet. This property was known to the Greeks, and now you can also see one very interesting experiment. This is a magnet. When this iron ball is placed here, it also becomes a magnet. So now this is a spherical magnet, and let us try to draw the magnetic field lines with the help of all pins. We can take all pins, and let me allow to, this is a all pin, and this all pin is representing the magnetic field line. We can have this all pin here, we can have this all pin here. There is a magnetic field in the surroundings of this ball, and all these all pins represents the direction of magnetic field. So this is a beautiful pattern of magnetic field lines. So regardless the shape of the magnet, every magnet has two poles, one is north pole and one is south pole. There may be another type of magnets we can see, and Dr. Alok will show you the magnets. This is a U-shaped magnet. It is used in number of experiments in school lab. There is another magnet which is very much familiar in children's, and they say that this is the play magnet or toy magnet, and this magnet also has two poles. When I bring this magnet like this, they attract. So these are two opposite poles. There is another magnet we can see, it is a cylindrical magnet. So different types of magnets you can have. This also have two poles. This is cylindrical magnet, this is U-shaped magnet, this is oval shaped magnets, toy magnets, this is a ring magnet, and I have already made this as a spherical magnet. When I put this like this, so it becomes a spherical magnet. So different types of magnet we can see. Now this phenomena of magnetism is related to the electricity. It was very interesting, and Joseph Henry and Michael Faraday independently, they have performed number of experiments, and they have concluded the outcomes of their experiments, which is known as Faraday law. Faraday showed that the EMF produced in a circuit due to changing magnetic flux with time is directly proportional to the negative rate of change in magnetic flux. We can write E is equal to minus d phi by dt, where phi is the magnetic flux. Magnetic flux means the number of magnetic field lines passing through a circuit, and mathematically we can write it as phi is equal to BA cos theta, where theta is the angle between magnetic field B and normal drawn to the surface. Then we can also say that area vector. And here you can see, that is the first one diagram, the circuit or the coil placed in magnetic field, the arrow is the direction of magnetic field and second arrow is, that is pointing out, represents the area vector. So theta is 0 and flux becomes B into A. In second it becomes BA cos theta, because theta is the angle between magnetic field and area vector. Here negative sign in the expression of induced EMF shows that the induced current and EMF are in such a direction as to prevent any change in the net number of lines of flux passing through the cross sectional area of the circuit. This is also known as Lenz law. So Lenz law states that the induced current or induced EMF opposes the cause of production. Let me take one example. When current is passed through a solenoid, it produces magnetic field. Here you can see a solenoid of length L, number of turns N. The magnetic field produced by the solenoid is N times of mu naught I upon L. N is number of turns, mu naught is magnetic permeability, I is the current passed through the coil and L is the length of the solenoid. If R is the radius of the solenoid and direction of current is changed in a very small time t, the change in flux will be B into A, because B into A in one direction minus B into A in another direction. So it becomes 2 times of B into A, or you can say 2 times of N times of mu naught I, that is magnetic field, and A pi r square, that is area. So this is the change in magnetic flux. You can find now the induced EMF, that is minus del phi by del t, rate of change in magnetic flux. It will be equal to 2 times of N mu naught I pi r square upon time t. So this is the expression for induced EMF due to change in direction of current in a solenoid. To produce induced current, change is must. Let me take another example. A bar of mass m and length L moves on a 2 frictionless rails in the presence of uniform magnetic field directed into the plane of the paper as shown in the diagram. The bar is given an initial velocity v naught to the right and is released. Let us find the velocity as the function of time. We know that force experienced by current carrying conductor in uniform magnetic field is IBL sin theta. In the case of sin theta is equal to 1, we can write minus IBL. This negative sign is due to the opposite direction of velocity and force experienced, and this force is called magnetic force, and here theta is the angle between magnetic field and direction of current. So in place of force we can write mass into acceleration, that is ma is equal to minus IBL, but I is equal to E upon R, that is EMF divided by resistance, which is written as VLV upon R. Here L into V is the area swept in time t. Thus in place of acceleration we can write dV by dt. So m into dV by dt is equal to minus B square L square upon R multiplied by velocity. We can rearrange the terms dV upon V, that is equal to minus B square L square upon mr into dt. Also we can write dV upon V in this form, and now we can take a log. So log V upon V naught is equal to minus B square L square divided by mr into t, and now I can reduce it as minus t upon tau. this is the velocity in function as a function of time. Now, we can talk some other phenomena related to the electromagnetism. As we have seen that current carrying conductor produces magnetic field. So, if we are changing the current, magnetic field also changes. And now Faraday experiment we can perform in a very simple way. Here we have a galvanometer and there is a coil inside the galvanometer. These are the two terminals of the coil of the galvanometer, and now these two terminals are connected. So, the circuit of the coil is closed circuit, and when a magnet is brought very near to the coil, you can see the change in the position of the needle of the galvanometer, which indicates that there is a current in the coil of the galvanometer, and this current is produced due to the motion of this magnet. When I move this magnet, magnetic field linked with the coil changes, means the magnetic flux linked with the coil changes and induced current is produced, which is indicated by the needle of this galvanometer. If I put this magnet stationary here, there is no change in the position of the needle of the galvanometer. So, there is no current. Current is produced only when there is a change in magnetic flux, when there is a change in magnetic field. If I do it fast, the deflection increases. It means this induced EMF or induced current depends upon rate of change in magnetic flux. This was the main experiment of Faraday.
So, on which factor the induced EMF and induced current depends on?
Your question is very important questions. Here when I put this magnet stationary,
Okay.
there is no induced current, but when I move this magnet like this, there is a change in magnetic flux, and this change in magnetic flux with time changes the position of the magnetic galvanometer needle, that is the presence of current in the coil of the galvanometer. When I move it fast, the deflection increases. So, when I move it fast means rate of change in magnetic flux increases. So, it depends upon rate of change in magnetic flux, not only on magnetic flux, rate of change on magnetic flux, and this rate of change in magnetic flux can be increased by increasing the number of turns in the coil also,
Okay.
by taking the strong magnet also, by moving the magnet or the coil relatively fast. So, here there is a change in magnetic flux to produce induced current, and Lane says that this induced current opposes the cause of production, as we have earlier stated.
Thank you, sir. You came here. I hope our learner will be benefited to this program electromagnetism, and I hope they will consume the energy accordingly their need, and they will save the electrical energy in our day to day life. Thank you, sir.
Thank you, and message for this discussion is to save electricity.
Thank you.
प्रकाशित करने, राहों को आलोकित करने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने। हम
अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने।
जीवन ये प्रकाशित करने, राहों को आलोकित करने।
सीमा से विद्यालय जो मुक्त हो, धन साधन समय की सीमा से विद्यालय जो मुक्त हो।
कभी पढ़े हम कहीं पढ़े, वे विषय की लोच से युक्त हो।
कभी पढ़े हम कहीं पढ़े, वे विषय की लोच से
और जागे,
मंजिल आने की ध्वनि सुने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने।
जीवन ये प्रकाशित करने, राहों को आलोकित करने। परीक्षा का अवसर एक बार ही क्यों मिलता फिर दुनिया में इसके केंद्र बात।
कोई मन चाहा केंद्र चुने, हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने। कोई मन
हिंदुस्तान के हर कोने में नौजवानों के पास प्रतिभा है, उन्हें अवसर चाहिए।
NIOS देता रहा है युवाओं को अवसर आगे बढ़ने का। NIOS से पढ़ने वाले इन युवाओं ने किया है संस्थान को गौरवान्वित। दिव्यांगों ने बन के दिखाया है सबल और आत्मनिर्भर। NIOS के साथ आप भी जुड़िए NIOS के संग।